So this problem is about the conditional expectation of random variables. So we have two random variables x and y whose joint probability density function is kxy over some region which is defined as y is bigger than 0, less than x, and x is less than 1. And we are required to find firstly the value of k, which is a constant, and then we need to find the expected value of x given y equals to y. This is also known as the conditional expectation, or sometimes as the minimum mean square error of x given y equals to y. So let's draw this region first where the probability density is defined. So if this is x, this is y, and this is the line y equals to x. So y has to be less than x, meaning we are in this lower half, and x has to be less than 1. So here x equals to 1. So this means the probability density of x and y is defined in this region. So in this region, fxy of x and y is equals to k times x and y, x times y. So for the first part, we need to find k. That means we know that fxy should integrate to 1 over this region if it is a valid density function. So that brings us to the condition that the double integral of this fxy, which is k times xy, we could take the x first and then dy. This should be equals to 1. So integrating over x first, meaning we draw a horizontal line here parallel to the x-axis and figure out that x equals to y here and x equals to 1 here. So the limits of x are from y to 1, and y goes all the way from 0 to 1. The reason is because this point here is 1. So computing this integral should give you the value of k, which is the constant. So let's do this, integrating over x first. So what happens is k can go outside. We have the integral from 0 to 1. Integrating over x will give you y times x squared over 2. The limit is from y to 1 dy. This should be 1, which tells you k times 0 to 1 y over 2 times 1 minus y squared dy equals to 1. So k over 2 y squared over 2 minus y4 over 4 from 0 to 1 equals to 1, which gives you k over 2 times 1/2 minus 1/4 equals to 1, which effectively gives you k over 8 equals to 1, so that means k will be 8. So that's simply the normalization constant that makes this fxy a valid density function. The next part is to find the expected value of x given y is y. So by definition, so it is expected value of x, or given y is some y. So in essence, it's just the expectation of x. The only thing additional here is that we have this condition. So what changes is just we use the conditional density instead of the density of x. So we will need the integral of, again, x here and the dx, because it's the expectation of x. The only thing that is different is instead of fx of x, we will have fx given y of x given y. And again, the limits are for x. And as we've seen in this picture, if you integrate with x first, the limits are from y to 1. The limits will be from y to 1. And obtaining this conditional density is simply the joint density fxy of xy divided by fy of y. So we know the joint density. What we don't know is just this marginal fy of y, which we can compute by integrating x. So this fy of y will be simply integrating x from the density, which is kxy. So if k is 8 and we have xy, if we integrate this over x from x is y to 1, we'll get fy of y. So that this makes it 8 times y times x squared over 2 from y to 1. So this cancels, it becomes 4. So it will be 4y 1 minus y squared. And of course y is from 0 to 1. So what we are left with here is the integral y to 1 x times fxy is 8xy, and fyy is 4y times 1 minus y squared. So this cancels to 2, the y cancels, so we will have dx here. And notice that the variable of integration is x, so y terms can go out. So we are left with 2 over 1 minus y squared, integral from y to 1 x squared dx, which is 2 over 1 minus y squared x cubed over 3 from y to 1, and this evaluates to 2 over 1 minus y squared, 3 here, and this will be 1 minus y cubed. So we're almost there at the result, which says expect value of x given y equals to small y is 2 times 1 minus y whole cube over 3 times 1 minus y squared. So that's the result.